This is a bell curve, also known as a normal curve. In a bell curve, we have symmetric sides that are asymptotic, which means they get real close to this x-axis, but they don't actually touch it on either side. And the probability, which doesn't really mean much to you, on the inside equals 1 or 100%. This line in the middle is going to stand for the mean. The 1 refers to the line that could be drawn right there, meaning one standard deviation above the mean. Remember, mean, mu, standard deviation, sigma. So then 2 standard deviations would be mu plus 2 standard deviations. The same with mu plus 3 standard deviations. Going in the other direction, the -1 would still be using mu, but we would be subtracting mu minus a standard deviation. For -2, meaning 2 standard deviations below because of the negative there, mu minus 2 standard deviations. And again, mu minus 3 standard deviations. Let me give you an example of what I'm talking about. If you are between -2 to +2 standard deviations, that's considered usual. The data fits into what would be considered normal, pardon the pun. If you are, not you, but the data piece is between -2 and -3 standard deviations, or +2 and +3 standard deviations, that's considered unusual. What about those 0.3 that are beyond the 3 sigma limits? Very unusual. More than 3 standard deviations from the mean is very unusual. I can relate to that. Instance, that my class took a test, and I found that the average score was 75, with a standard deviation of 5. That would mean that the mean here in the center, the average score would be 75. If I added 1 standard deviation to that, I would have 75 plus 5, or a score of 80. If I added 2 standard deviations to my 75, 75 plus 2 times 5, which is 10, for 85. Plus 3 standard deviations would be the mean, plus 3 times the standard deviation, which would be 15, for a total of 90. Going in the other direction, if I subtract a standard deviation, my mean minus the standard deviation of 5 is 70. Minus 2 standard deviations would be 75, minus 2 times the standard deviation, which becomes 10, for 65. Minus 3 standard deviations would be 75, minus 15, because it's 3 times sigma, and sigma is 5. 3 times 5, 15. Answer, 60. In case you're wondering, why would I ever do anything like this? Consider the test. If I wanted to know who's getting an A, I would know that it's the students who earned over an 85. Who gets a B? It's the students between 80 and 85. Who gets the C? Well, lots of people. Anyone who's got between a 75 and 80. And those that are below the mean, but still within one standard deviation, also get a C. Likewise, the D's are between 65 and 70. In my purples, from 65 and 60, those are the people who are going to flunk this particular test. Because this is a normal curve, normal being what we normally relate to, there are consistent percentages. The middle, one standard deviation above and one standard deviation below, each take 34% of the inside of the curve, for a total of 68% being within one standard deviation. Between 1 to 2 takes up a total of 13.5% each time. Therefore, from the mean to two standard deviations above and 2 standard deviations below takes 95% of the curve. The last little bit gives you a total of 99.7% of the curve, meaning 2.35 between 2 and 3 standard deviations above and 2 and 3 standard deviations below. What this does is it gives me a consistent estimate referring to my prior grading situation. 2.35% of the class should get A's and F's. 13.5 should get a B. 68% should get a C. 13.5 should get a D. Here's an example. Instead of grades, let's look at the mean value of homes. And the value is approximately 125,000 with a standard deviation of 5,000. We're not only going to map this out, we're going to answer a question about estimating the percent. Using the numbers that are given, mean being 125, adding a standard deviation of 5 to get 130, adding another standard deviation, adding another standard deviation, going back to the mean, subtracting the standard deviation from the mean to get 120, subtracting another to get 110. The question is, what percent of homes are between 120 and 130,000? Well, as you can see, it's in the purple. What percentage was that? A total of 68%. The average weight of newborn babies is bell-shaped with a mean of 3,325 grams, standard deviation of 571 grams. The question is asking, what percentage? So we'll have to use those consistent percentages from the empirical rule, the 68, 95, and 99.7. The mean in the middle would be 3,325. If I go one standard deviation above, I'm adding one standard deviation. So I would have mean plus one standard deviation. 3,325 for the mean, plus 571 for the standard deviation. Rusty trusty calculator tells me 571 plus that 3,325 gives me a 1 sigma limit, as it's properly called, because we have 1 and a sigma, 1 sigma limit. Very creative, I know. Sorry I didn't come up with it myself. My second sigma limit, above the mean, I would be taking mu plus 2 times the standard deviation. 3,325 plus 2 times 571. Rusty trusty calculator tells me 4,467 for the upper, meaning above the mean, 2 sigma limit. My third sigma limit, mu plus 3 standard deviations, would be 3325 plus 3 times 571 for an answer of 5,038. But I have to backfill for my lower sigma limits, meaning mu minus sigma. 3325 minus 571. 3325 minus 571 equals 2,754. That's a 4. Two sigma limits, meaning subtract 2 sigmas. I'm going to show you a shortcut. If I take my lower number from my 1 sigma limit and I subtract another standard deviation, that gives me a total of 2 standard deviations. So mu minus 2 sigmas is really 3325 minus 2 times 571, or a whopping answer of 2,183. Now if you're thinking to yourself, self? That's the number I'm looking for. You're right. For clarity, I will go ahead and subtract my last sigma from that to get my third sigma limit, just so nobody says I didn't do it all the way. 1612. But what I'm really looking for is the percentage between the second sigma limit, which was the 2183, and the 4467, which was the upper sigma limit. Let me color. Why? Coloring. There. That's colored. You're asking what percentage is shaded in red. Well, if we go back to the percentages between 2 sigmas, we would be looking at above and below 2 standard deviations. We're going to go out and find from here to here, also known as 95% of the curve would be covered. 95% of those babies way between those amounts.
Let's try an example and see if you can relate. A standardized reading test is given to 10,000 high school students. The scores are found to be normally distributed with a mean of 500, standard deviation of 60. If a score below 440 is considered to indicate a serious reading deficiency, about how many of the students are rated as seriously deficient in reading comprehension? Our empirical rule percentages are listed at the top. The mean is the center. Mean plus sigma is 560. The mean mu plus 2 sigmas becomes 500 plus 60 plus 60, or 620. Mu plus 3 sigmas is 500 plus 60 plus 60 plus 60, or 680. For the lower limits, the mu minus the sigma. For the lower 1 sigma limit, 500 minus 60 is 440. Now we're talking. Those are the parts of the problem that I'm looking for. Mu minus 2 sigmas, 500 minus 60 again, is 380. And the lower 3 sigma limit, 500 minus 60 minus 60 again, is 320. Now what percent meets the criteria of being less than 440? The 2.35% plus the 13.5%, for a total of 15.85% of the people who were in the study. Multiply that 0.1585 times the number in the sample, 10,000, for an answer of 1585. 1,585 people are considered reading deficient in this particular sample. Another example. Suppose you were informed that the annual income for teachers is normally distributed bell curve, with a mean of 35,000 and a standard deviation of 5,000. What percent would you estimate for the teachers with incomes over 45,000? What percent would you estimate to have an annual income of less than 30,000? Bell curve, start with the mean. Add a standard deviation. 35,000 plus 5,000 is 40,000. Add a second standard deviation. 35,000 plus 2 times 5,000, or 10,000. 45,000 is my upper 2 sigma limit. Add the third standard deviation. 35,000 plus 3 times the 5,000, or 15,000. 35,000 plus 15,000 is 50,000. That's my upper 3 sigma limit. My lower limits, subtracting the mean, would be 30,000, mean minus 1 sigma. Mean minus 2 sigma, 35,000 minus 10,000 is 25,000. And the third sigma limit, this one below the mean, 35,000 minus 5,000 minus 5,000 minus 5,000 is 20,000. Now we can answer the question. For the first part, we want to know those that make more than 45,000. 2.35 according to our empirical rule. In the second part, we want to know those that make less than 30,000. We've got two percentages to put together, those between 3 and 2, those between 2 and 1. Total, 2.35% plus 13.5% is 15.85% would be my estimate